Okay, we're off. So I'll turn things over to group five.
Good morning, everyone. Welcome to our design presentation. We are Yeehaw Dispensers, and we're here to show you our design for a canisterized satellite dispenser, or as we like to call it, our cowboy satellite dispenser. This is our team consisting of Alessia Venturi, Nathan Nichols, Nicole Kirshner, Taylor Morrison, Ali Shams, and Rachel Roble. During this presentation, we will go over the problem provided from our customer, our team's mission statement, an overview of our product and subsystems, some key highlights of our design, and our budget breakdown. The mission of our customer is lunar exploration with imaging satellites mission. This involves a surveying of the lunar surface in order to identify landing points for spacecraft. The main problem provided by our customer is the need to dispense a 12U CubeSat into lunar orbit at 2 meters per second. The CSD must protect the CubeSat during the launch and up until deployment. The CSD should provide this housing and launching mechanism, with further design specifications coming from NASA standards. Our team's mission is all about modularity. To summarize how we came to our mission, we look at the three-circle model. Our team's passion is all about preserving the right of the user to repair their own products and easily interchange parts. Our economic engine is driven by selling our CSD at a lower cost by minimizing the amount of manufacturing and permanently fixed parts. Finally, we believe we are the best at providing easy to assemble by using the skills we've learned as students.
Okay, so as a product overview, here we have a picture of our CSD. It's shown here with the door open and the CubeSat will fit snugly inside. We have decided to break our product into 4 main subsystems. That is the launch mechanism and circuitry subsystem, the door mechanism, inner housing, and outer housing. The overall design has a mass of 4.99 kilograms and global dimensions of 271 millimeters by 271 millimeters by 403 millimeters. And it is designed to fit a 12U CubeSat to the specifications that we received from our CubeSat team. So the first subsystem that we want to go into more detail on is the launch mechanism and circuitry subsystem. This consists of 4 parallel springs and a force plate that serves as the launch mechanism. And then we have an Arduino controller and a DB9 connector that serves as our circuitry aspect. As you can see here, this is a cross section of our design. You can see where the CubeSat fits in. It rests on top of the force plate, and beneath that is the springs and the controller. And overall, our entire design has 27 customer needs, but these are the ones that we have decided align most directly with this subsystem. So some highlights of this include need 1, which says that we need to launch 1 CubeSat as a co-manifested payload. Need 15, which says that we need to be able to communicate with the launch vehicle and send and receive signals. Need 18, which specifies that the CubeSat needs to be deployed with an initial velocity of 2 meters per second. And need 26, which relates to the CubeSat power requirements. There are 3 deployment switches located on the CubeSat that need to be inhibited during flight in order to keep the CubeSat powered off until it launches. So going into the launch mechanism half of this subsystem, like I said, we have a spring-based force plate. So you can see here, one of the walls has been removed from our CSD, so you can more clearly see this subsystem. And we also show it with the force plate and without, so you can get a better view of the springs. So the CubeSat sits on top of an aluminum force plate. As you can see, we have some circular cutouts in the force plate. This is because the CubeSat is built with tuna can sized components on the bottom, and so we need to make room for those. And we have decided to use 4 springs in parallel. Each spring is rated for 1,900 Newton per meter spring constant. And in order to launch the CubeSat at 2 meters per second, the springs will have a compression distance of 0.046 meters. In earlier iterations of our design, we used one spring with a greater stiffness, but instead we opted to use 4 parallel springs, and of course the spring constants would add together instead, because having 4 springs will better ensure that the force plate stays level and the CubeSat doesn't end up getting jammed if it launches out skewed. And it also allows us, because now we have a greater spring constant, we can decrease the compression distance and therefore decrease the overall length of the CSD, eliminating unnecessary mass. And we also it also makes our design flexible, because if the customer did want to launch the CubeSat at a different velocity, you can exchange the springs for something stiffer or less stiff, or you could cut them to a different length.
All right, as for our controller, we selected a Arduino Uno Rev 3 microcontroller, which has already made it to space on some CubeSats, and it has also the microprocessor on it. The ATmega 328P has been rigorously tested by the European Space Agency. As for, there were concerns about the controller being bolted straight to the bottom plate, as you can see in the bottom image. But we ended up solving this problem by putting in a polyimide insulating layer between the two. And now we don't have to worry about the vibrational loads. I will note that the polyimide insulating layer is pretty commonly used on aircrafts for dampening. Next slide. Okay, as for controller and circuitry, we'll move kind of right to left. So right is the big picture. We're looking at all the connections and the board, right? So we specifically have, we're taking in power data from the launch vehicle, and we're going into our controller, and then we're running it up to our pin pooler, which has a memory shape memory alloy. So we have the connections up to the pin pooler are splice connectors that are to the National Aeronautical Standards. And then as for our connector to the launch vehicle, we have a DB9 connector as seen on the far left, and that is bolted into the plate so that we don't have to worry about cables moving around. The DB9 connector has screw pins, so you can tighten the cable attachments. We have that just in case NASA has different standards for what signals are sent where. And also, again, modularity is really nice. The last thing I want to note is that we used fairly standard coloring for our cable so that it's clear to the engineers installing. So black is ground, red is power, and then arbitrarily we selected green to be our data. Next slide. Okay, and then as Nikki mentioned earlier, we need to have 3 deployment switches inhibited on the CubeSat so that it does not turn on during like after it is installed and before launch. So our group didn't per se give us the exact locations of it, but we used the NASA standards. So as you can see in green, these are some of the locations that are commonly where the buttons would be commonly located, and we have accounted for them so that we can press the buttons. Next slide.
All right, up next is our door mechanism, which consists of 5 major parts: a vented aluminum panel door, a pin puller to keep it in place, a mount for the pin puller, and a shaft and hinges for the door. Next slide, please. Here's an overview of the customer needs that we deemed were relevant to the door subsystem. The highlights are that the door has to allow the CSD to vent and equalize the internal and external pressures. It must protect the CubeSat from contaminants. For example, at one point we considered a concept for the door in which there was no door, the CubeSat was just exposed, but obviously that would conflict with this need. The door must open in under 2 minutes, and the door cannot release, or the CSD as a whole cannot release anything into lunar orbit. So another idea, for example, that we had for the door was glass door that would shatter to release the CubeSat. We couldn't go with that idea because of this metric. So getting into some details, for the pin puller, we went with the EBAD TINI pin puller for a number of reasons. Some of the more important ones are that it's lightweight, It's qualified for space applications. It doesn't use any pyrotechnics, and it can withstand the loads that we need it to. The actual opening and rotation movement of the door is done by the CubeSat. The door closes in on the CubeSat, which also forces the springs to compress. And then when the pin puller lock is released, CubeSat is launched as the springs decompress. I'll talk more about that in the next slide, but one benefit to note from this mechanism of using the door as both a door mechanism and also as the launch mechanism for releasing the CubeSat is that we reduce the number of electrical components that would be needed, and that could fail compared to if you had a separate door and a separate launch mechanism. As you can see here, the maximum door opening time was estimated to be 468 milliseconds, which is well under the 2-minute maximum. It's worth noting that this time doesn't include the time it takes for the Arduino to receive and process commands from the launch vehicle, but this time shouldn't be significant, and it should be a repeatable and easy to account for time. So this slide briefly shows how the pin puller mechanism works. While the door is closed, the pin is in its initial position of being outwards, as you see circled in the picture on the left, the top left. And when the pin is out, it goes through the holes on the mount, which is slightly transparent in these images, and the hole on the door, holding the door in place like a slide latch lock. Once the Arduino controller gets the signal from the launch vehicle to open the door, the pin puller retracts the pin, as shown in the image on the right. And now there's nothing anchoring the door down from this side, so it's free to open about its hinge, and it gets pushed open by the CubeSat, which was sitting on that plate with the compressed springs. So in summary, the springs decompress, the CubeSat is pushed out, which pushes the door open. It's also worth noting that the mass of the door is negligibly small compared to the mass of the CubeSat, so we assume that the door won't have any effect on the CubeSat's launch velocity. And as far as the process of putting the CubeSat into the, as far as putting the CubeSat into the CSD, it's basically the same process reversed. You put the CubeSat in, slot it in the rails, close down the door, add the pin puller. This slide shows some calculations justifying the selection of the pin puller and the sizing on the door latch. In these pictures, you can also get a better look at the motor mount and how it interacts with the pin puller and the door latch. The factor of safety for the transverse load acting on the pin is calculated here at about 1.8, which seems very reasonable. The factor of safety on the latch, on the axial force pulling the latch in tension, is fairly high, but as you'll see, we generally went for much higher factors of safety on the door mechanism, since it's such a critical mechanism. It's responsible for both protecting the CubeSat and also making sure it doesn't get released too early or too late. And also it's a very dynamic subsystem, especially once it opens, and you want to make sure that it can handle all the stresses that you throw at it. Speaking more on the door panel itself, the door contains 3 slot cutouts to allow for venting and to allow for the pressure in the inside and the outside of the CSD to be equalized. Those slots are also great because they help us reduce the mass a little bit. And the direction of the slots is chosen to minimize any addition of stress by including them. So for example, if you had included them, or if the slots were included going the opposite direction, then the stress would be increased because of the direction that the stress is acting along. As you can see here, we calculated a factor of safety from yielding from the bending stress of 2.71, which is maybe a bit high, but it's still fairly reasonable. And then talking briefly about the shaft and the hinges. The hinges are secured on either side by 2 Phillips screws, and the shaft is fit inside the cutouts on the hinges. Here we mentioned that the door is designed to lose lots of energy in a collision with the CSD. What we're talking about here is during the launch, it's possible that the door could open so fast that it spins all the way around and hits the CSD or the launch platform. And if that happens, there's a risk that the door could rebound and block the CSD again before this CubeSat has had a chance to get clear of the CSD. So we tried to minimize the speed at which the door would potentially rebound. Here you can see we calculated factors of safety for the shaft, the axial and shear stresses on it. Mildly interesting note, the shear stresses are actually, it's more likely to fail in shear than in tension, which is not usually the case, or not usually the case in our design. Bending stresses were usually significantly larger. And then as a final comment on the high factors of safety, designing the components with such high factors of safety is probably a notable contributor to why our mass was so close to the maximum limit. It's definitely possible that if we designed with smaller factors of safety, our mass might be noticeably lower. But with the assumptions made in the designs and the potential for unaccounted for or unpredictable conditions, they don't seem overly unreasonable, especially on the largest contributors to the mass, which would be, for example, the door panel.
So the third subsystem of our design is the inner housing. The structural frame of the inner housing consists of a base plate and guide rails. The base plate has channels for the 4 springs of the launch mechanism to attach to, and the plate is bolted onto the outer housing. The bottom of the guide rails are welded to the base plate, and the top of the guide rails are secured to the outer housing with bolts. The guide rails hold the CubeSat in place throughout the mission and guide the CubeSat out of the CSD when it is launched. The installation of the inner housing is an aluminum coated black captain. Next slide. Next slide. Is it frozen for anyone else?
Yeah, I think Nikki has just dropped, I think.
Oh, okay.
My internet just cut out. Put it back up right now.
Okay, sorry.
You're good.
Okay, perfect. So here you can see an overview of the customer needs pertaining to the inner housing subsystem. The main needs to address are the shock, acoustic, and thermal loads that are applied to the system throughout the mission. The aluminum coated black captain is the main feature that protects the CubeSat as well as the CSD from shock and acoustic loads by providing dampening, and the insulation protects the CubeSat from thermal loads as well. Based off of customer need 13, the CSD must house one Lewis. Can you go back, please? The CSD must house one 12-unit CubeSat, which it successfully does, and the guide rails are the feature that hold the CubeSat in place throughout the launch. Next slide. So one key feature to note for the CubeSat rail design is the use of standoff screws in between the insulation and the rails. The black captain is not a rigid structure and the rails are positioned against it. So by adding a stand-up screw, we're able to maintain a constant position of the rails. And this just helps to ensure that the CubeSat has a constant trajectory throughout the launch. The outer housing, the insulation, the standoff, and the guide rail are secured together using screws. Next slide. So the main parameter to be analyzed for the inner housing is the thickness of the insulation that we used. So we first calculated the minimum allowable thermal resistance required to regulate the thermal loads that the CubeSat would experience. And as you can see, that result is on the bottom left-hand corner. We then calculated the thermal resistance to the walls provided by the insulation when having a wall thickness of 9.6 millimeters. I think it's important to note that we ended up using 6 sheets of the insulation where each sheet had a thickness of 1.6 millimeters, which gave a total thickness of 9.6 to use in this calculation. So the thermal resistance was calculated as 0.32 square meters kelvins per watts. And then dividing this thermal resistance by the minimum allowable thermal resistance gave a factor of safety against the thermal loads of 11.2. This factor of safety is relatively high, and based off the calculations, our design is capable of protecting the CSD from thermal loads based off of the chosen insulation and thickness. Next slide. We then completed an acoustic analysis on the sheets of insulation using the natural frequency equation that's shown below. While performing this analysis, the main assumption that was made is that the insulation sheet was a thin plate that's clamped on all sides. This resulted in a natural frequency of 3,722 hertz. And then we compared this result to NASA's standard for vibroacoustic loading, and it passed the criterion. So therefore, our design satisfies the metrics set forth by the customer in relation to the acoustic loads. And then for the shock loads, a similar process was followed where the insulation sheets were treated as a thin plate that were clamped on all sides. This produced the same result using the same equation. And then this result was compared to the shock response standards in the SLS manual, and it passed the criterion as well. Next slide.
Our next subsystem is the outer housing subsystem. We used hollow aluminum bars in a welded skeletal design. We acknowledge the difficulties that come with welding aluminum, but due to mass constraints, we felt it was our best option for our outer housing. Next slide. These are the customer needs that relate to our outer housing. Some of the main ones that we'll discuss in this presentation include the structural load, vibration, and thermal environments, as well as the center of gravity or center of mass. Next slide. So we completed structural loading analysis on the frame, which showed that the weakest section of the structural frame is still able to withstand 291.239 G-force. This makes it more than suitable for keeping shape under extreme forces during launch. It's also important to note that this occurs during along its weakest direction, as well as, and this showcases the strength and robustness of our structural frame. We also did vibrational calculations on the frame. We treated each bar of the outer housing as a beam bound on both ends, and then used that to find the stiffness using the equation shown in the slide. Then we use the natural frequency equation shown also in the slide to find the natural frequency of each bar, and then compared those values to the vibroacoustic loading criterion in the NASA standards to confirm that the frame was within functional vibrational load range, which it was. Next slide. We did thermal analysis on the aluminum that makes up the frame to confirm that it was within survivable thermal range. And some of the calculations are shown on the left side of the slide. We also found the center of mass of the outer housing in order to confirm that our design would preserve the functionality of the launch vehicle, which is shown in the top right, in the X, Y, and Z directions. We also wanted to mention some mounting options for mounting our CSD to the secondary payload canister brackets of the launch vehicle. So that could include using brackets or welding. Next slide.
All right, and then let's talk about how they all interface together, right? So again, to emphasize modularity as a main component of our design choices, all of the connections, including bolts and nuts, and then also our splices for our cables, they're all reversible minus the splice connectors. However, as a solution for like testing, you could use Wago connectors. And then once you are certain that everything is good, you could use the splice connectors. I also want to note that all of our bolts and nuts, and also we use PEMSerts as some of our nuts. So they're flush to a lot of our plates, right? So all of those meet the National Aeronautical Standards. I also want to mention, right, that we plan to use thread locker to keep our bolts in once we are also certain that our design is complete and we're ready to go and send it off to NASA. The last thing is we will be including lubrication. So there'll be some lubrication between the shaft and the door. And then we're also planning on putting lubrication on the rail guides so that the CubeSat, there's less friction between the CubeSat and the rail guides. Next slide. All right, and I kind of briefly mentioned it, but we're using PEMSerts, and this was something that was introduced to us during our design review too, and we ended up really loving it just because it's flush and it means there's less like external components, and yeah, it was very helpful for us just because we wanted to make sure we had no interferences. And on that topic, actually, I will mention that, sorry, Nikki. On that topic, I'll mention that we also switched a lot of our bolts to button heads, simply so that we would have, well, we're not going to have interferences, but in case there were any of those, you know, there'd be less issues. Next slide. All right, and then this was mentioned earlier, but we have channels for the springs, right? Instead of welding them so that we could interchange them depending on the customer needs for the initial velocity. We also want to mention that we're environmentally friendly. So most of our parts are off the shelf, but the parts that are not off the shelf that are custom manufactured are all aluminum, which is our aluminum 661 T6. And that is recyclable. We also have it so that some of the parts require large blocks. And because of that, we can cut some of the material off from the large blocks to make some of our smaller pieces. We also kept in mind that we We're not using aerosols or combustibles, toxic materials, or pollutants, just so that our workers and anyone interfacing with the CubeSat is safe. Next slide.
For our design, it is necessary that a functional prototype is made prior to full-scale production, since the budget is limited and accurate testing of vibrational, acoustic, shock, and thermal loads would require the use of more expensive materials. The inner and outer housing systems are neglected as they would require more expensive materials. This makes the door and the launch subsystems the main focus of our prototype. This allows us to ensure that our model can accurately dispense the CubeSat at a desired velocity and orientation, while also guaranteeing the door mechanism is capable of opening within the time, as well as to prevent the door from rebounding. The full-scale production run includes the amount of a production of 10 CSDs. This number was selected as our production run as it allows the occupation of a majority of the SLS spacecraft that the CSDs are mounted to, as well as it allows for discounts on products that would help reduce the overall cost during the mass production of the units. Although the budget is listed as $500,000, this included the cost of labor, manufacturing, transportation, salaries, and all purchases made for the production of the 10 units. For the goal of our design, we set the production-related tasks to be a limited budget of $50,000. This allows us to accurately pay 6 engineering salaries of our team, as well as other miscellaneous labor costs due to transportation and external testing, as well as $30,000 for transportation and storage. For the production model, it would still be important to test the other subsystems after the first unit is made. The budget allows for testing after the full-scale production to ensure the CSDs are operational and space-ready. Due to the modularity of our design and the independence of the subsystems, the testing can be done throughout the manufacturing and assembly of the design without the need for full construction. The subsystems costs here reflect the prototype and production costs separated by each subsystem. Here it is important to note the extreme cost of the inner housing on the production run. This is due to the pricing of insulation materials being expensive. However, our calculations show that the insulation is worth its extreme cost and is vital to the survival of the CubeSat during the launch. The door and the launch subsystems are also price-heavy components, as this is where the moving parts and electronics are located. These features are critical to test to ensure that they work in order to prevent loss. The allocation of the prototype budget is done accordingly in order to accurately represent this. The miscellaneous materials cost listed in the production run model is for lubricants and thread locker to be applied for extra security in the final model. For the budget, it is important to recognize the impact of the cost of labor and manufacturing in the design process for the production run. With labor and manufacturing, it is approaching half the cost of the entire production run. This pie chart also highlights the extreme use of off-the-shelf parts and the minimal need for manufacturing in our design. This emphasizes our mission of modularity and shows how our components are quick to manufacture and assemble. This is further reflected with the lower percentage of the cost of the manufacturing component. The total cost for the production runs approaches $30,000, well within our expected budget.
So this has been our canisterized satellite dispenser with a focus on modularity and ease of assembly. I'm so sorry, my computer is about to die. I apologize if that suddenly happens. But we've been Yeehaw dispensers. We'd like to specifically thank the panel as well as our sponsors and anyone else that's been able to attend this presentation. Next slide. Any questions? I'm going to plug in my computer.
All right. Awesome. Thank you for the presentation. Let's open to questions and comments from the panel.
Hi guys, this is Tom Singer from Northern Grumman. I'll start out saying good job. This interesting presentation, interesting project. The first thing I'm going to pick at is slide numbers, because that would make all the rest of these questions much easier to help you refer back to specific slides. So in the future, if you can add slide numbers, that'd be great. But we'll do our best. The one major thing that jumps out at me is I didn't see a physical interface to the CubeSat in your design. Is there something holding that CubeSat in place during the launch?
Sorry, can you, yeah, thank you, Nikki. When you mean holding it in place, can you reframe the question? So,
Yeah,
'cause if
so
it's,
yeah, there's going to be a CubeSat that's in your container,
Mhm.
and presumably it's, you know, without any sort of mounting, physical mounting between the CubeSat and your container, that thing's free to rattle around inside your container. Is that the case?
yes, so
Or am I
no.
misunderstanding something?
So this picture is actually really good at demonstrating it. If you see in the center of like the image, there are 2 rails. So they're in every corner. Our CubeSat, or at least our aerospace team, said they would be using a rail system. So we hold the rails in place, therefore it's not going to like rattle around. And then also the distance between the door and the launch plate, there's essentially almost no distance because the launch plate is trying to press it up.
All right, so you're going to constrain lateral motion with the rails, and you're going to constrain the vertical motion just by like squeezing it up against the door?
Essentially, yes.
Okay, that concerns me. The lateral, yeah, I think that makes sense. Relying on like that spring pressure to keep it up against the door, I'm concerned that is maybe loading a satellite in a way that it is potentially not designed to be. The other concern that I have there is your door, and having a door that is being pushed open by the very closest point to the hinge of the door. I don't know if you guys have ever tried to open a door by like pushing on it near the hinges. That's much more difficult to do than pushing on it out near the door handle, right? So you're going to put a significant amount of load into your satellite again in a location in a manner that satellite is probably not naturally going to be designed to handle. And certainly you could probably design a satellite to handle that, but like I definitely wouldn't want to be pushing a door open that close to a hinge.
So we did ask our aerospace team and they were okay with it, but I do understand the concern with it being close to the hinge. I mean, torsional springs could be added back to the door so that once it's released, it could flip back out.
Yeah, I would love to see that door open on its own rather than being pushed open. And one of the other reasons is all of a sudden now you've got this like sort of side load acting on your satellite as it's trying to be ejected, right? And that's going to cause a satellite to kind of like rack in the container, which is going to introduce extra frictional loading and stuff that is potentially interfering with the deployment. So I would be happy to see some sort of modification to that system. Other things going on, those are like monstrous springs. You know, if you look at like the coil springs on your car suspension, you're at something like 200 pounds per inch. And I did the calculation because I don't know metric very well, but 12,000 newtons per meter is something like 105,000 pounds per inch. Like these are very, very stiff springs. And I'm wondering, I guess the intent is that you can achieve your required velocity with a very small compression distance. Is that what's driving that spring stiffness?
Yes, I would say so.
Okay. What's the acceleration of the satellite going to be when those springs are released?
I'm not sure.
Okay, that's something I'd want to know. And the only thing holding that compressed in your current design is the door being latched closed and again squeezing the CubeSat down?
Yes.
Okay. Interesting. That concerns me somewhat. Let's see. You'd mentioned your Arduino little control board down there is isolated against vibration.
Yes.
And okay, so you got a natural frequency of your polyimide is 0.
Yes.
I'm not sure, number one, that I believe that, and I'm not sure, number two, that I believe that the overall acceleration on the Arduino is going to be like 0 hertz. Like it's going to move, right? And it's going to shake
Yes.
a little bit in a launch environment. So I don't know that just saying, hey, it's 0, we don't have to worry about it, is sufficient there.
Yes. I don't know if
You-
yeah, I was say Taylor, if you want to talk a little bit more the assumptions with this.
Based on this was more so an assumption based on our limited abilities in terms of testing for the time being. And we were hoping in the future, if with making a prototype, that we'd be able to more accurately test that. And it would hopefully not require too much material to ensure limited vibrational load. But due to the limitations that we had in terms of calculating the vibrational loads, we found that this was in line with our other calculations in terms of assumptions due to the insulation.
Okay. Can you flip to a slide showing your door? There we go. That like 2 back was perfect, or even this, the bottom right. Yeah, this is where I'd like slide numbers. Yeah, so this bottom right image. How are you planning on manufacturing that door? Is that going to be one solid piece of aluminum?
Yes, that door would be, ideally, it would be one solid piece of aluminum, and like we mentioned, it would have to be a pretty thick piece of aluminum. But one of the benefits of our design and having it all made of the same components is that it's not like that entire block just goes to waste. We can cut out pieces and make other components like the hinges.
What other
out of-
components are you going to make? I mean, as a guy who is admittedly not a manufacturing engineer, if I showed this design to a manufacturing engineer, they would probably have a lot of impolite words for me. It would be very difficult to cut that block in a way that's going to save that material to repurpose. And just given that design, a much better way to do that is make the flat part out of a flat piece of aluminum, right? Just get flat stock, and that's your door. And then the latch, whether that needs to be riveted on or welded on, or however else you want to do that, would be a much more efficient use of material.
Yeah, I can understand that perspective.
Let's see, what else do I have? I'll go back to like dynamic kind of stuff. You're talking about like the natural frequency on the outer frame. Somewhere near the end. Yeah. Yeah, there it was. And so I think I understand what you're doing is that you're saying, all right, well, if we take each individual bar in this frame and say, okay, we're constrained on the ends, we've got a natural frequency of whatever the natural frequency is. I'm assuming it's very high. And saying, okay, all those natural frequencies satisfy whatever our criteria is. Is that the analysis that was done?
Yes, it compares to a graph that shows that it needs to be below 20 hertz or above 2000 hertz for
Yeah, I would assume they're all
vague
well above
assumption.
2000 hertz. Is that right?
Yeah.
Okay. The natural frequency response of the individual pieces of that frame is going to be significantly different than the natural frequency response of the frame as a whole. So I would encourage you to analyze that structure as a whole rather than as a collection of individual pieces. And kind of the sanity check on that, right? If I have a whole bunch of really short beams, right, they're all going to have really high natural frequencies. But if I weld them end to end and make a very long beam out of a bunch of very small beams, right, now my very long beam is going to have a significantly different natural frequency as a whole than the natural frequency of any of the individual components.
That definitely makes sense.
Okay. right, I'll turn it over. I'm sure Dr. Traum has questions about like the thermal analysis, so I'm gonna let some other folks chime in.
I think Juliana actually had a question about thermal analysis.
Surprisingly, yes, I actually have multiple questions. Overall, it's a really good presentation. I like that it was concise, but I did have some questions. Can you go back to that area where you show the insulated Arduino? I think this one's, yes. So have you done any calculations on the temperature around and what's going on in space around your Arduino in this system that you have here? I am concerned about the temperatures and Arduino just not being able to work since the temperature might drop really low or instead go high.
That's entirely valid, and due to time constraints, no, but it will make it into our final design report. And I mean, the installation may also change for that reason, so.
Okay, so it's on the back of your mind. Okay, another thing that I've noticed is, can you go back to the full design overall looking line? I think one of the pictures. Yeah, this. So it looks to me that those three gaps are what's supposed to be vent in it. In the door?
Yes.
Yes. So venting is important during ascending, but how do you make sure that nothing comes out as the cleaning requirement? And the second one, those should be vents that prevent backflow. So they should allow their depressurization. Sorry, I can't speak this morning, but they can't allow this stuff to come in.
I will comment at least on the contamination. So the thought, based on the SLS handbook, assuming that we're on the SLS, is that as soon as after this is manufactured, as long as we have cleanly manufactured this, no biological contaminants, when we send it over to NASA, NASA will be keeping it and with HEPA filters at all times, and there should be no other contaminants entering.
Okay. What about this working in space and the inside depressurization, something breaks? Do you have anything that would prevent it from just going out in there in the space?
Or reframe. So you mean if anything breaks inside
Within
the
your
CSD,
inside, yes, right
and then
after
it leaves through the vents.
right after your CSD is deployed, sorry, the CubeSat is deployed. Is there anything that prevents the insides from going out?
Arguably no, but I will suggest that because all of the components that were likely to fail or like small pieces that could exit would be underneath the CubeSat. So in that sense, none of our components would fly out before the CubeSat has exited. Now, of course, if anything was broken, the CubeSat exits, then yes, things could come out with it. Ideally, nothing would.
Yeah, okay. But yeah, I suggest you look into the vents that prevent backflow instead of this, just mainly as from the conversation with Dr. Generali, he did mention that depressurization is important and required, but you can't allow stuff to go in. And the final question that I have is, you were talking a lot about natural frequency and there were numbers in the 3,000, 4,000, and I understand there that trapezoid of death, just like Dr. Traum called it earlier, that satisfies it. But I also remember we have a requirement from the SLS planner's guide, table 520, about the shock environments, where your things, your parts that are having about 3,000, 4,000 hertz frequency going to experience 3,000 G force as a shock load. Have you done calculations that explain that you can survive that?
I may be mistaken. I will definitely leave room for that. But I did do calculations based on the Kapton aluminum layers, 6 layers of them. And so there's definitely some assumptions that had to be made regarding like the material the material properties that I used to try and make sure of that, but I tried to compare it to like the yield strength of aluminum to assure that it would not, and I found that it wouldn't. I may have had some problems there. But I, at least in my calculations, saw that it would not fail, especially in the 6 layers.
Okay, yeah, it would be nice to see that in the presentation, especially when you're saying about their shock loads, it confirms, but how you confirmed it, that would be nice to see. But overall, I think you've covered everything, at least in my boxes. So thank you.
Thank you.
Okay, and looking at the time, and it's actually we're a minute over. So, and I have a bad habit of just going over and staying over. So let's maybe wrap it up there instead of continuing, so that we're responsive to everybody's time, sensitive to everybody's time. So any final questions or comments from? Oh, it looks like Juliana's got one.
In fact, I do. I really liked your customer needs, the tables that you have, but it also would be nice to include your aerospace design customer needs or your decision in here. At least that would explain why your decisions were made the way they were.
They are included, at least like if you see, oh no, Nikki, go back.
Sorry, I thought you
Yeah.
were talking about something different.
Oh, I mean, you can also go to the appendix, but like need 26 here, that is a need specifically given to us by the aerospace team. And we have some others that are included. Our new
We probably
customer
could
needs
have we probably could have iterated that during
Yeah.
those. So we do appreciate
Yeah.
that
yeah,
feedback.
we will do
That's
that,
good
but
news.
we do have it in it.
Okay, great. Thank you.
Very good. Okay. Yeah, so let's wrap it up there, just so that we don't go too far over. Just want to thank you guys for sharing your presentation with us this morning. And I think you guys did a great job. This was a really strong group all the way through the design reviews. You guys brought a lot of creativity and energy to the project, which I really appreciate. So I think we'll close off there. Let me hit the record button so that we stop recording.